Example: sodium surface is illuminated with the UV light, okay, with the wavelength equal to 300 nanometers. For the part A, find the maximum kinetic energy of the photoelectrons. So we just want to find the Kmax. Okay, we know what? We know that the wavelength equal to 300 nanometer, and we know that the metal is the sodium. Okay, so now for the sodium, it means that the work function equal to the 2.46 electron volt. Okay, let me take a note here. The work function of the sodium equal to 2.46 electron volt. Okay, so we just want to find the Kmax. Then which equation should we use? Right, we have two equations to find the Kmax. We have this one, and we have this one, right? But now this question is not related to the stopping potential. Okay, so then let's use this one. The Kmax equal to the energy of the photon, right? And then minus the work function. So let's use the Kmax equal to the HF and then minus the work function. So don't forget that the HF here is the energy of the photon. So let me use a symbol as the normal E, okay, for the energy of the photon. Now we know the wavelength. Okay, we know the wavelength. We know the wavelength of the photon. We just want to find the energy. Then let me use this equation. Okay, let me use this equation to solve for the energy. So it said that the energy in the EV equal to 1240 electron volts nanometers, and then over the wavelength in the nanometer, okay, equal to 1240, right, electron volt times nanometer, and then over the wavelength, which is equal to the 300 nanometer. Then we can get the answer to be 4.13, okay, 4.13 electron volt. That's mean the energy of the photon. Okay, so now just plug in this into this equation. Then we have the 4.13 minus the work function, which is equal to the 2.46. Okay, then the answer is 1.67 electron volt. So this is going to be the maximum kinetic energy of the photoelectron. Okay, also let me take a note here. Let's say that also, okay, the stopping potentials is, okay, so we say that the Vs, right, equal to, from this question, the Vs equal to the Kmax and then over the E, okay, but now the Kmax just equal to the 1.67 electron volts and then over the E. So now you can see that the electron charge, right, just cancel out, and then we have the stopping potential to be equal to the 1.67 volts. Okay, so this will be the stopping potential in this case. Now for the part B. Okay, for the part B, what is the cutoff frequency of the sodium? So we have only one equation to find the cutoff frequency, which is the Fc, right, equal to the work function and then over the Planck constant. Let's use this one. Fc equal to the work functions and then over the Planck constant. So now we have the work function in the unit of electron volts, okay? But we just want to find the frequency in the unit of the hertz, which is the 1 over the second. So in this case, let's use the Planck constant in the unit of electron volts times the second, which is this one, okay? Which is this one. Let me copy it first. Equal to, okay, so let's just plug in. We have the work function equal to the 2.46, right, electron volts, and then over the Planck constant in the unit of the electron volts times second as well. So now you can see that electron volt just cancel out, okay, and we have the 1 over the second left, which is equal to the hertz, right? And then this value, okay, this value is going to be equal to the 5.95 times 10 to the 14 hertz, okay? So this is answers. And then also we can find the cutoff wavelength. So let's just say the cutoff wavelength. Okay, so let's say lambda c for the cutoff wavelength is going to be equal to the c, the speed of the light in the vacuum, and then the cutoff frequency, okay, which is equal to 299,792,458, right, meter per second, and then over the frequency, the 5.95 times 10 to the 14 hertz, which is the 1 over second, right? So now the value is equal to the 5.4 nanometer, okay? It means that if we charge the light with the wavelength which is larger than this value, okay, or it means that the frequency is less than this kind of frequency, so then no photoelectrons emitting out from the metal surface. But then on the other hand, if we charge the light with the wavelength less than this value, so in this question, right, we just charge with the 300 nanometer, okay? If we charge the light with the wavelength less than this value or the frequency greater than this value, so we can have the photoelectrons emitting out of the metal surface. Okay, another example. A student studied the photoelectric effect with the two types of the metals. Okay, we have the metal A and metal B. The experiment showed that, okay, number one, for the same incident frequency, the stopping potential of the metal A is greater than the stopping potential of the metal B by the 1.48 volts. Okay, then let's just write down as equation first. So we see that the stopping potential of the metal A is greater than that of metal B. Okay, so minus the Vs sub B by the 1.48 volt, right? So now number two, the cutoff frequency of the metal A is the 60% of that of the metal B. So we have the cutoff frequency of metal A, right? It's going to be the 60% of the cutoff frequency of the metal B. So we have 0.60, okay, of the FC of the B. So here we have the two equations from the questions, right? Okay, so we just want to find what? We just want to find the work functions of both metals. So we just want to find the work functions of the metal A and metal B. So it means that in this case, we need two equations. Okay, we need two equations to solve for the work function of the metal A and metal B. So how should we start? Okay, let's just start from Einstein equation. Let's just start from this one. The HF equal to the Kmax plus the work function. Okay, so we have the HF equal to the maximum kinetic energy and then plus the work function. So we know that we charge the light with the same frequency, okay, with the same frequency here. Okay, so it means that the work function of the maximum kinetic energy of the metal A plus the work function of the metal A, right, must be equal to the maximum kinetic energy of the metal B and then plus the work function of the metal B. Okay, so we get this equation. But then what is the maximum kinetic energy of metal A and metal B? Okay, what is these two values, right? We have the relationship that the Kmax equal to the E times the work function, right? The stopping potential here. Okay, so in this case it means that we can just write down these two in the terms of the stopping potential. We have the E times the Vs sub A and then plus the work function of the A, right, equal to the E times the Vs sub B and then plus the work function of the metal B. Okay, and also we can link this work function to this frequency as well. Okay, let me just write down here. We can get that, okay, the FCA, right, we said that the work function equal to the frequency over the H. Okay, so in this case we have that the work function of metal A must be equal to the work function equal to the 0.60 times the work function of the metal B. Okay, so now we have this equation and we have this equation, right? And also this one can be converted to the E times the VSA, okay, and then minus the E times the VSB, right, is going to be equal to the 1.48 electron volt. Okay, and that's it. So now we have these three equations and then we can just solve for the phi A and the phi B already. Okay, so let's do that. Now if I just move the EVSB, right, to the left hand side, so then we can get that the EVSA minus the EVSB, so it's going to be this term, right, which is equal to the 1.48. okay, and then plus, so now let me just move let me just plug in the first the phi A into this equation. Okay, then it's going to be the 0.60 and then times the work function of metal B, and then equal to this one, equal to the work functions of the metal B. So then finally we have that the work function of the metal B, okay, is going to be equal to the 1.48 and then over, okay, if you move this to the right hand side, it's going to be the 1 minus 0.6, right, equal to 0.4. So we have the 0.40 here, which is equal to 3.7, okay, just equal to the 3.7 ohms in the unit of electron volt. Okay, so don't forget that this one is still in unit of the electron volt here. Okay, so then this must be electron volt as well. Okay, so now we got the first answers. Now for the flux A, right? For the flux A, the flux A just equal to the this one, okay, equal to the 0.60 and then times the wave function of the B. Sorry, it's not the flux, it's just wave function. The 3.70, okay, which is equal to 2.22 electron volts. Okay, so this is going to be the answers. Okay, another examples. Okay, part A. If the average frequency emitted by the 200 watt light bulb is equal to this value, okay, so here we know that the frequency of the photon equal to the 5.00 times 10 to the 14 hertz, okay, and then the 10% of the input power is emitted as the visible light, okay. Okay, so approximately how many visible light photons are emitted per second? So we said that the power of the light bulb, right, equal to the 200 watt, okay, the power of the light bulb equal to the 200 watt, sorry, the 200 volts, the 200 watts here. But we said that just only the 10%, right, of this power is the visible light. So it's this frequency. So it means that the power, right, of this visible light of this one, of this frequency, is going to be equal to the 10%, right, the 10% of the power of the light bulb here, which is equal to the 20 watt. Okay, we just want to find what? We just want to find how many visible light photons are emitted per second. Okay, so we just want to find, okay, the number of, okay, let's say the number of the photons first, right, equal to, okay, so if we know the energy of the visible light, okay, so let's say that if we know the energy of the visible light, okay, and then if we know that each photon, okay, each photon will have the energy equal to the HF, okay, so let's divide it by the energy of each photon. So if we have this ratio, right, we can guess the number of the photons, okay, so remember we said that the energy of the light, right, is just equal to number of the photons and then times the energy of each photon, okay, so then we can find the number of the photons from this relationship. But now the question is, we just want to find the number of the photons, right, per second, okay, per second. So it means that let's just divide this by 1 second, okay, by 1 second, and then again let me just divide this by 1 second as well, okay, on the left and then on the right. Okay, so let's look here. We have the energy of the visible light per second, okay. What is this? It's just the power of the visible light, which is equal to the 20 watt, okay. So then here we can get that equal to the 20 watt, and then over the energy of each photon, right? So let's use H times the F. the Planck constant, okay, 6.626 times 10 to the negative 13, and the frequency, right, just equal to this value. It just the 5.00 times 10 to the 14, okay. Okay, so then let me take the one out. Okay, so then can get that equal to the 6.03, right, times 10 to the 19 electrons per second. Okay, so this is the answers. So now for the part B. Oops. Actually, it should use red. Okay, so now for the part B. At what distance would this correspond to 10 to the 11 visible light photons per square centimeters per second if the light is emitted uniformly in all directions? Okay, so let's say that if we have a light source here, we have the light bulb. How to draw something like this. Okay, we have the light bulb, right? And we said that the light just emitted in all directions. Okay, and we want to find what? We just want to find the distance, right, from the point source, okay, or from the light bulb, right, that have the 10 to the 11 visible light photons per square centimeter per second. Okay, so let's say that this distance okay, so let's say that this distance is just equal to r, just equal to the r, right? Then from this sentence, okay, from this sentence we can get that the 1.00 times 10 to the 11th, okay, so number of the photons, right, per, oops, sorry, actually my bad, this must be the photons, not electron, sorry about here. Okay, number of the photons per square centimeter per cm square, okay, and then per second, right, per second here. It's going to be equal to, okay, so let's say that this is the surface of the sphere, okay, so the area is the 4 pi r square, okay, the 4 pi r square, and here we have, okay, the 6.03 times 10 to the 19, right, 10 to the 19. So then with this we can just rearrange the equation to get the r here, right? So here we have that the r, okay, is going to be equal to no, let me move to this, then we can have more space, and this will be the photons per second. Yep, I think this would be better. Okay, then we can have over r, right, it's going to be equal to, okay, so let's just put in the number, the 6.03 times 10 to the 19 photons per second. Okay, so this value, and then move this one to the right hand side, and then over the 4 pi, and then times the 1.00 times 10 to the 11th photons per cm square, and then times the second, right? And then finally just take the square root here. Okay, equal to, so now you can see that this unit, right, just cancel out, and we have the centimeter square to the numerator here, and then take the square root out, we get the centimeter as the unit of the radius of the circle or of the sphere. And now just use calculator to compute this value. Okay, so we have equal to 6930 centimeter, okay, or just equal to the 69.3 meter. Okay, so this going to be the answers. Okay, it means that we need to detect the photon at this distance from the light bulb here.